Hello, everyone. Thank you for coming. My name is Hazel. I am a senior data scientist. Oh my voice suddenly came out so much louder. I'm a senior data scientist at a Microsoft partner called Blue Fragments, and today I will be talking about deep learning implementation, so frontiers of AI and machine learning. It sounds very dramatic, but basically I'm going to be talking about neural networks. So, as I mentioned earlier, I work for a company called Blue Fragments, and today I'll just go through a few examples where recently innovative applications of deep learning have been used, as well as a little bit about the history of machine learning and how it's reached the point that it's at today. So to start off, we have in the 1950 the very famous Alan Turing's Turing test, where is it possible to build a machine that is so realistic that it can deceive humans into thinking it is another human being. And then in 1951, Marvin Minsky created SNARC, which was basically stochastic neural analog reinforcement calculator. It was very simple. It was just a very basic tether to neural networks where it just sent in an input and passed it through to an output, and it just determined whether there was a probability of it coming through. And that was it. In 1957, the very first perceptron model came through. And then my introduction to machine learning and to artificial intelligence came in 1997 with IBM's Deep Blue. And this is because growing up, I had a father who was obsessed with chess. And for those of you who are not chess fans, 1997 was when Deep Blue, the machine, beat the world champion in chess. And my father had a massive fit about that. Artificial intelligence is the worst thing ever. It's destroying humanity. And to just put the icing on the cake, his daughter works in artificial intelligence. So, you know, it makes Christmases very awkward sometimes. But yeah, that was when I learned that a machine could actually beat a human, and I became fascinated with that. So from there, we reached the 2000s, and there's an enormous growth in the world of machine learning. And this is when deep learning really starts to reach its potential because of the incredible strides that occurred in technological advances, things with GPUs. Before that, the demands were just too rigorous to run these huge neural networks, and so it just wasn't really much of an option. Once it became possible with the new technologies, that's when you saw this enormous growth in companies like Amazon, Facebook, Google, all of them using this to their great advantage, along with other machine learning capacities like AdaBoost in their backend. Now, this is a very simple neural network. It just shows that you have a simple input layer. In between, you have a hidden layer, and then you have the output layer. So you have all of the inputs in let's pretend that we have a data set, and you've got all of the features. They all get funneled through into the hidden layers, and then the output would be, for example, the one column that is featured as the Y column, and then it goes that way. There is some disagreement, but in general, most people follow the mindset that deep learning neural networks are such that they have 2 or more hidden layers, and that's the standard baseline. There are some really nitpicky data scientists who will argue with that, usually academics, just because, you know, they have to write papers and argue with each other, so that's just how it is. You can see that I left academia a long time ago because that wasn't my thing. Now, deep learning, as I mentioned, is part of machine learning. It's a subfield that was really developed in the 2000s because of the changes in technology. It features enormous neural networks, and the classic example, the one that I just showed you, is the multi-layer perceptron model. So you would just add more hidden layers into the model that I just showed you. From the multi-layer perceptron model, you also have other types. The 3 standard bearers are recurrent neural networks. They're very similar to multi-layer perceptron models. It's just that they have a temporal component. So you can think of it as sort of within the hidden layers, the information that gets passed through in a traditional neural network just goes this way, straight. There's no loops in it. No data from this hidden layer can ever go back. But in a recurrent neural network, that's exactly what you have. You have loops in time that can actually retain information. Now, you also have convolutional neural networks. Those are such that they actually have a spatial component, and they're very often implemented in deep learning systems that involve images, video, because it can retain a topography of a system. It can really understand those kinds of things. And it's also very useful, for example, in writing, because writing and music, they also have a sort of topographical underpinning to them. And so that's also an area where it gets implemented. But the baseline is the multi-layer perceptron model. And one of the most interesting applications of actually all three of these is in the field of medicine. So a little bit of history on medicine. Full disclosure, my background is as a physicist. I did not like my chemistry classes. It involved way too much memorization, and I'm not great at that. That's the wonderful thing about physics classes, is that if you forget something, you can just sit there in a panic and derive stuff all the way back. So this is not my forte. But in the world of medicine, one of the things that they have for development of drugs is that they have in vitro testing and pretty much never anymore in vivo studies. So that's where you actually test in a living human being. This is more like back in the day when Madame Curie would just run around and get exposure to radiation, that kind of thing. That was what they were like, but now not so much. So it's either in vitro, or what they have now is also in silico studies. And in silico studies are essentially using computers and computer simulations. So a lot of the time they will use very traditional statistical modeling, just old school mathematical models, heuristics. But one of the things that they've discovered is that implementing machine learning can be incredibly valuable, and because they're working in the world of chemical spaces, it becomes even more valuable to use deep learning, because deep learning has that capacity, like I said, when it comes to convolutional neural networks, to map topographies. The other really great thing about it is that, generally speaking, people in the world of medicine are not highly trained in the world of data science. So when it comes to things like feature selection, feature engineering, these are not their fortes. It's not what they spend all their time doing. One of the benefits of deep learning is that the area that a lot of data scientists spend their time on, which is the feature engineering along with the pre-processing of the data, you can kind of hack it a little bit when you're working with deep learning systems, in the sense that they can really pick out patterns and develop systems that will actually generate pretty solid predictions without the very carefully orchestrated feature engineering that you need when you're doing something, say, with a logistic regression. In cases like that, there's a high sensitivity support vector machines. You really have to think about how long it's going to take to train them, and the kind of features that you're going to have in them. So that's where you will follow very traditional means of things like feature selection with greedy backward and greedy forward selection, where you're dropping off the least relevant features. Or you'll do things like you'll have regularization, and you'll use an L1 regularization. And that is a really interesting case where it uses pure mathematics, and it determines which features have a very strong correlation with your output. So you'll have your Y column, and then when you use L1 regularization for a test run, say on a traditional logistic regression, it can actually tell you, so all of these features drop to 0 or really close to 0 very fast, whereas these retain a value which tells the person who's working with the model that those that have dropped to 0 are probably less relevant. There's not as strong of a collinearity to the Y value. And that's the kind of stuff that you have to think about when you're working with a lot of other traditional machine learning methods. Whereas in deep learning, you still benefit greatly from doing that, because it just improves the accuracy and streamlines the model that you're working with. But you don't have to be quite as rigorous, and you can still get very good results just because of how they work. The downside, of course, is that when you're working with deep learning, you're working with a black box times however many hidden layers you have. So it's not like a decision forest or a decision tree where you can actually click in and then see the baseline, follow the patterns that are actually telling you this is what we're using to determine the final value. Is this a yes or a no? Is this a true or a false? Is this value class A, B, C, or D? That kind of thing that you can do with a lot of traditional machine learning models. You can't really do that because neural networks in general are black boxes. And so that's just something that you kind of have to accept, that you're not going to be able to fully immerse yourself and understand the pathways that the models are taking you in to reach their conclusion. But regardless, it still is a type of machine learning that allows for advances that are very, very challenging with any traditional methods. And medicine has found that that is actually the case. So, for example, as I mentioned, in medical studies, when they're developing drugs, they actually have a very long, arduous process. And they very recently did calculations in 2017, and they found that for a single drug to pass through the traditional process, and these are, of course, based on statistics that were found in the United States, but they're generally pretty applicable around the world. A single drug cost $1.8 billion from beginning to end. That's the cost to get it through all the way to the end. And on average, it takes 13 years. When it comes to things like neurological problems, it's even more complicated and even more challenging to get it through. And those take over 20 years, which if you have a degenerative illness, those 20 years can be the difference between life or death. So the great thing about using computer simulations and using machine learning is that there are certain areas of medical studies and medical research that are very, very inefficient when they use traditional means. And this is where virtual screening becomes super important. Traditionally, what they do is they have a process called high throughput screening technology. And this involves very expensive, very laborious processes in specific laboratories. These laboratories have to meet very specific baselines, and there's very few of them. And then as they're running through it, it's really time-consuming and it's very, very costly. And what a lot of studies have found is that, for example, in one traditional run-through on a chemical, what they would find is that running through all of these different chemicals to see if the result was acceptable, they would have 0.02% that had some possibility of going forward, and this was just in the initial test run. Whereas if they did virtual screening in the beginning, they could increase that all the way up to in the 30 percentile, which is an enormous cost-cutting measure, and it also really speeds up the process. And so this is something where they've become really, really interested in working with machine learning, because what machine learning can do is it actually can do research on already existing drugs to see if there is any kind of how would I put it? So what you can do is you can take the chemical structure of a drug. You can actually use it to the mapped protein spaces that humans have already in existence that they know about. And then what they can do is they can test it to see if it matches with a high probability the possibility of actually working with this other illness. And that's actually something that they do a lot these days, because getting a brand new drug onto the market is so laborious and so expensive. What they'll often do is they will test old drugs to see if, well, we've got 20,000 proteins, all of which may have some kind of issue on them. Can we test each and every single one of these compounds that are actually legally usable in the world, and see if they might actually have the possibility of impacting positively one of these other areas. And so that's something that they can actually use these virtual screenings using machine learning to determine whether or not that is actually valuable. And they have actually done this on several occasions. So one of the interesting cases where they've actually worked with it is AMP-C beta-lactamase. I don't know if you guys know about the gram-negative bacteria, the superbacteria. They're immune to, what are they called? Antibiotics. Thank you. For some reason today I can't seem to remember my English. I'm thinking in Spanish, which is not good. So so they're immune to antibiotics, and they have actually been using a lot of these virtual screenings and research to see if there are actually ways of inhibiting it so that you can actually beat the superbacteria. And they use these enormous databases that can run through all of these chemicals. For example, there was actually a gentleman whose name was Coscosas, who ran a test. It was not on the gram-negative bacteria, but it was actually on 7 traditional pub chem structures of chemicals, running to see if it could map with a high level of accuracy. And what it found was that when it was used against traditional stochastic methods and also traditional machine learning methods, the deep learning networks were always the ones that had the highest accuracy ratings. So just on that alone, a gentleman who did not have a huge amount of experience with machine learning or deep learning systems was able to hit much higher accuracy levels in this area, which is incredibly valuable because not every single person working on these particular medications and potential drugs has the capacity to call up a data scientist or a developer who also has machine learning expertise and get them to come in and dive deep into these things. Particularly because there's just too many compounds and it's just too expensive to spend that kind of time on every single potential compound. But deep learning kind of neutralizes or flattens the playing field to a certain extent so that they can actually test and see there is potential here with the machine learning, and then if they move forward with these particular drugs, then they can actually call in people who can really specialize and pull the information into a good structure that can be used in more accurate machine learning methodologies within virtual screening. So that's one of the areas that I found that they have been doing work in that was really, really interesting. They've really started to pour in money into convolutional neural networks in particular because, again, they have that topographical capability. Their spatial knowledge is incredibly useful when it comes to mapping chemical compounds. And so seeing how those match with already pre-existing drugs on the market could be invaluable in the future. The next one is NASA, which shouldn't be too much of a surprise. NASA's always playing with frontier stuff. And this is actually in the field of exoplanetary discovery. I don't know how many of you guys know, but when it comes to exoplanetary research, what a lot of astrophysicists tend to do is they tend to have a whole lot of graduate students who spend a laborious amount of time just sitting in a dark room, going through these transit photometries, like they're just seeing light curves and seeing these dips, tiny, tiny dips, and trying to figure out, oh, is that another star just looping in front of it, or is it potentially an exoplanet? And they just spend years and years and years on that in the hope that maybe one of those will actually be an exoplanet with which they can publish a paper, do their thesis, and finally escape the basement. That's the kind of thing that they work on. So there was a team that decided that they were going to use machine learning to try to save the day for these poor, suffering graduate students. And what they did was really interesting. There's two traditional methods. There's radial velocity, but one of the favorites is the one that I just mentioned, transit photometry, which is just, you've got a star, you have a light curve, which is just detecting the amount of light that it's emitting, and it's just keeping track over a very extensive period of time from KEPLER to see whether there are any dips, and whether those dips match the patterns of an exoplanet or potentially another star, or if it's just bad data, if it's just KEPLER acting up and it's noise that's coming through. And a lot of the time it is noise. The interesting thing about this particular one is that they actually discovered two planets that they had not been able to discover before. So one was the rocky planet on Kepler 90I. This was based on a traditional artificial neural network. It was a convolutional neural network, yes. So they were actually mapping the spatial patterns of the light curves. And what they found with this one was that there was a really interesting planet that was circling the star every 14.4 days. So it's very hot, it's really close to the star, and it's actually very small. And traditional methods had not been able to detect it. And then what they also found was that in another Kepler environment, they discovered a second star. And in this one, it was actually able to it managed to hit the solar system number of planets detected. So now there's somebody that's rivaling us, and that's Kepler 90. The reason why I'm actually bringing this up is not so much because NASA astrophysics, it's cool. It's actually because when I was reading through the documentation, through the scholarly writing about this particular study that was done with machine learning, I found several really interesting things that were going on. So one of the things that they discussed was the fact that when they were running with a convolutional neural network, what they did was they took a set of data that had been checked through and reviewed by human beings. And it was quite well done, very well set up, very neatly streamlined and separated into into a simple binary classifier. One is these are highly probable to be exoplanets and all the rest. And when they ran through a lot of the tests, a lot of the systems, what they actually managed to get was they had a convolutional neural network that hit 98.8% accuracy, which is amazing. And so they were super excited. They had this fantastic binary classifier, deep learning neural network. It was performing great. They did the traditional cross-validation, which means that you've got the data set, and you've got a test set, and you have a validation set. They were super proud, and they were talking all about that. And then they discussed how they actually acquired data from KEPLER on simulations. And these simulations were actually generated, there's huge amounts of them, and they are based on very carefully constructed actual data on exoplanets and on binary passes. So binary transits are where you've got one star and you have another star looping in front of it. And when they ran this test, instead of their beautiful 98.8% accuracy, what they actually found was that when there was one batch, which was of actual simulated exoplanet transits, it was only 81% accurate. And when they actually tried to detect whether something was a binary transit, that means a star passing forward, it was only 33% accurate. And so there's a long spread in the paper where they're trying to discuss why this could be, how is this possible, and like you have this model, it's so beautiful, it's 98.8% accuracy. How did we go from 98.8 to 81% when it comes to the exoplanets and 33% when it comes to determining that a binary transit is not an exoplanet? Because traditional methods, just on the binaries that are mathematical models, they can hit 67% accuracy. It's not great, but it's pretty good. And if you're a human and you're trained in these things, you will see that the dips, the shape of the curve, is such that you would say this is highly likely to be another star passing in front. It's not likely to be an exoplanet. And what this can actually come down to is very simple, and that is that there is always human bias. And that's something that we all have to think about when it comes to deep learning. Now, obviously, this talk talks about the how and the why of deep learning and these amazing advances that are going on with it. And it's true that there are a lot of really amazing things that are going on with deep learning models. There's a lot that can be done. But it's only as good as the understanding of the people who are working with the deep learning models. So it's quite easy to publish a paper that follows a very traditional, proper path for a test, where you've got the training set, you've got the test set, you've got the validation set, and you hit these really high accuracy levels. But it's also important when you are implementing it in real life, when you are deploying real models, to understand that if you are really engineering the data, or if you are being hyper-selective on the data sets that you're working with and that you're putting into the model is only as intelligent as the data that you put into it. So it's actually really, really important to think about the kind of data that is actually going to be flowing through that model. So in this particular case, the gentleman who did this did a fantastic job at doing the research, understanding the proper methodologies, but what they didn't initially think about was the fact that they needed to think about exactly what kind of images, exactly what kind of light curves were going to be coming through. It wasn't always going to be these very carefully selected, very well orchestrated light curves. There's going to be a potential bias if people are not very, very focused on understanding exactly how the data is going to flow in. So in these cases, you have to make a choice. And what that choice is that you're either going to have the data come through and be very heavily edited, very engineered, so that it will run accurately based on the parameters that have been established in the initial model. If not, then what you actually have to do is you have to train the model from the very beginning with the real-life data that's going to come through that is not going to be engineered. And sometimes that means that the models are not going to perform at the incredibly high levels of accuracy that people love to see. And that's the thing that's kind of tempting and very dangerous about deep learning, is that you can, if you structure the data sets that you run through it, get incredible levels of accuracy. I can sit down and within 30 minutes, I can pull up data sets, create a simple CNN, and hit 99.5% accuracy on a data set of just a few thousand images. And then I can go and I can say, look, boom, I did it. Binary classifier, I can determine whether there's a crack in the pavement or there's no crack in the pavement, or there's a crack in the construction or there's no crack in the construction. These kinds of things would be important if you're working in a construction company or you're working with some kind of development like material sciences and you're wanting to detect whether there's some kind of fracture in the images. The problem is that while you can do that, you also have to think about the reality that if you train that model on very heavily edited data sets that are very clear, that can hit very high performance levels, that's the only kind of data that it's actually going to be able to hit those kinds of baselines on. So you have to think about what you can actually do to the data. When it comes to things like images, are you going to be able to fine-tune the images to such an extent that you can actually reach those levels consistently? Or is it such that the data that's going to come through is going to be relatively poor, and so then you have to understand that there are going to be those weaknesses. And that's the kind of stuff that is actually really interesting and really challenging about deep learning, because it is very tempting to go into it, to think about the fact that the strength, the capacity that it has allows for weaknesses in feature engineering, in feature selection, in data processing, that kind of thing. You can actually get away with a lot, except that at the end run, when you're actually testing it in real life systems, that's when you start to see the cracks in the model that you've developed. And that's actually what's really interesting about seeing all of these tests, all of these advances in machine learning, all of these implementations that are going on outside of the world of data science, because people outside of the world of data science are taking deep learning, they're implementing it in new and creative ways, like in astrophysics with KEPLER, in medicine, as they're doing when it comes to drug testing. And they're discovering, as they're doing it, the weaknesses, the potential flaws in it that they need to think about. And it's also giving a lot of knowledge to those of us who work in the realm of machine learning, because it kind of emphasizes again that all of those baselines that people sometimes think that they can give up when it comes to deep learning, all of the grinding parts of data science, you can't really let those things go. Deep learning is not going to resolve all of those issues. You still have to have a very strong understanding of the data that's coming in, the structure, the background, the baselines that you're working with. And that's actually where, for example, data engineering, a lot of you work in software engineering, that's where it becomes so critical. The kind of data that's retained, the quality of the data, how it's stored, how it's labeled, all of those things are critical for developing and optimizing models that implement deep learning. So that was why I picked KEPLER 90. Plus, it was just cool. Yeah. Fun little planet, beating out or equaling the Earth system. And then KEPLER 80 was another one that the same team that had all these problems actually discovered. So they discovered an Earth-sized planet in the KEPLER 80 system, which was really interesting because it's actually very challenging for astrophysicists to detect Earth-sized planets that are in the Goldilocks zone, in the zone where it's potentially human habitable. And that's simply because the drops in the transit, in the light curves, when they're transiting across a star, are very, very faint. So there's just, by default, a trend towards having detections of very big planets, just because that's the kind of light curve drop that you can detect really easily. Machine learning will allow them to get a better idea once they work out some of the issues when it comes to the data processing. But machine learning will allow them to actually detect these very low-level systems, and that means that even with the weaknesses in the model that they had, what they could actually do is that they could actually set up a baseline of, we have 90% confidence that this might be a planet, we have 80%, 70%, 60%. They select those that hit those 90, 80 percentiles. They focus their attention on that because there is a high demand for time on KEPLER on being able to focus on a particular area of space. And then they can actually figure out eventually with enough data that yes, that is an exoplanet. We've got as high of an accuracy, high of a certainty as possible that this is in fact an exoplanet, and they can tick that box and add it to the population research that has been done in exoplanets for Kepler. And it also gives a better idea to scientists about the structure of the universe, so people don't get the impression that it's red giants everywhere, really close to stars. It's actually much more complex than that. So it's the kind of thing that with time and with more fine-tuning, they'll be able to really do some interesting things with the deep learning systems. And finally, I figured I would end on a high note, and that is during my searches for the kind of stuff that might be interesting that they're implementing neural networks on, I discovered Deep Beat. And this is for a study on musical creativity, specifically rap. So a team in Finland, had to be Finland, of course, decided that they were going to see if they could create a neural network, a deep learning model, that could generate rap lyrics. And when I saw that, I just thought, yeah, I'm going to have to talk about that one. I'm going to have to dig into this one. And it was fascinating because I discovered all kinds of weird, random stuff about rap that I never knew before. Case in point, there's this thing called rhyme density, which measures the high aptitude of a rapper, which apparently has to do with assonance, the rhyming of the vowels within the lyrics, and that they have actually done research and discovered that rap, of all of the musical structures that are in existence, is the one most closely aligned with formal poetry, which might explain why I've never enjoyed rap, because I never enjoyed formal poetry either, so it kind of made sense. Regardless, though, what was interesting was that they decided that because it has this very structured, formalized lyrical pattern, and also I think they're just rap fans, this was what they were going to do. And then they also did research into the mathematics of rhyme density and decided that they were going to implement that into the model so that not only would the model be generating lyrics following, an implementation that used, I think, 600,000 lines of music from 104 rappers. Along with that, they were going to implement this mathematical structure that gave priority to rhyme density, to the best type of rap. I also discovered that apparently Jay-Z is not very high on the list of rhyme density, but he's heavily increased. He was like at 3.2 in the past, or 0.32, and now he's elevated to like 0.4, so his rhyme density is getting better and better, and Eminem is actually relatively low in comparison. He's only like 0.37. These are the random facts that I discovered while digging into Deep Beat, and I'm never going to be able to get it out of my brain, and I'm not too sad about that, because this is fascinating. So they decided to implement a traditional neural network, just a multi-layer perceptron model. I'm pretty sure that the reason for that was time constraints, and also because I think they were just getting super excited about building a website that would actually generate rap lyrics that people could play with, and then they started getting requests from actual rappers in the United States and New York to read through and run mathematical tests to see how much rhyme density they had in their rap lyrics, to see how good is their musical capacity as a rapper. So pretty sure that's why they decided not to go with recurrent neural networks, because recurrent neural networks tend to be the default when it comes to written formats. So I'm sure that a lot of you have seen in your Gmail, if you've got the Gmail, that it keeps adding words in, giving you little tips. That's a lot of recurrent neural networks at play there. But they just used a traditional model. They fed through, and it was kind of like, they considered it sort of an information retrieval format. Based on deep learning. And so what they did was they tested it initially on a baseline, and that baseline was to see whether they could actually predict the next line of an existing song. And the assumption, and the baseline assumption is not quite right, but it's not completely wrong, is that the next line should be the one that is the best lyrically related to that sentence in the rap song. So it should have the most semantic connection, should have the most, how do you call it, assonance to that one as well. rhyme density, and thus it should select it out. And if it were a completely random model, then the model would work at 0.03% accuracy. That's how often it would select the next one for that model. They were super excited because they actually hit 17%. And given what they were working with, which is essentially playing with deep learning for a purely creative process, I actually thought that wasn't bad, especially for a team of Finnish, I think, bachelor students just having fun with deep learning models. And this is actually an area that's really, really interesting, is the idea of implementing machine learning into a realm that people would traditionally consider the arts. It's not something that most people would ever think of using machines in, something where you could potentially use a convolutional neural network to paint a picture, or you could use a traditional neural network to write a rap song, where you could potentially do a recurrent neural network to write Shakespearean verse. That's actually been done. And that's the kind of thing that I found really, really fascinating. So much so that I figured that I would conclude by doing this, showing you DeepBeat, where I spent a lot of hours just obsessing. And they give you a lot of options here, so you can generate a lot of lyrics. So let's just say that I'm going to pick something related to truth, and it's just going to generate lyrics. And as you can see, this is what it shows us. Let's see. When you see me, don't ask if the show's on. If you got to dump a few rounds, don't stop. I'm never going to be a rapper. But as you can tell, they've actually put it in live to test, to see whether or not people consider this these really good lyrics or not. And you guys can play with it too. And so that is the world of DeepBeat. And apparently I talked really fast because I was not expecting to wrap up this quickly. But there you go. Thank you so much. I hope you guys enjoyed. If you have any questions, please feel free to ask now, and I'll be happy to answer them.